Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and this is the conclusion of our lecture, the mean value theorem. When last we left off, you were solving this problem, determining all numbers C that satisfy the conclusions of the mean value theorem for the following function on this interval. I hope you solved this, but just in case not, I'll give you a chance to do it anew. You know what to do. Let's see how you did. Well, so what we need to do is f of x is a polynomial, so it's continuous and differentiable. And so that means that the mean value theorem is going to apply. So let's take the derivative. F prime of x, we're taking the derivative of this, is 3x squared plus 4x minus 1. Now we want to find the numbers that satisfy the conclusion of this. So that means we're going to say that f prime of c is equal to f of 2 minus f of minus 1 all over 2 minus a minus 1. So that means that 3c squared, I'm plugging into here, 3c squared plus 4c minus 1 is equal to 4. And if I turn that into a formula to use the quadratic formula on, I have this. So I use the quadratic formula and I get that c can be either minus 4 plus or minus the square root of 76 over 6. But you see, the c has to be between these two numbers, so we have to check. Now both of these numbers could be in between there, but if we checked, we see that this one is not. So the only answer is c is equal to minus 4 plus square root of 76 all over 6. Here's another problem. Suppose we know that f of x is continuous and differentiable on the closed interval 6, 15. Let's also suppose what we know that f of 6 is equal to minus 2, and we also know that f prime at x is less than or equal to 10. The question is, what is the largest possible value for f of 15? You know what to do. Let's see how you did. Well, the conclusion of the mean value theorem says that f of 15 minus f of 6, all divided by 15 minus 6, is equal to f prime at c. Now we also talked about having it look like this. And so what we're going to do is we're going to plug numbers in. And so what we're going to say is f of 15, I'm adding the f of 6 to the other side, plus f prime times this. So this is going to be minus 2 plus 9 times f prime at c. But we know that f prime at c is less than or equal to 10. So this is less than or equal to 10. So you see we have f of 15 is equal to this, is less than or equal to f prime at c is less than or equal to 10. So I do this calculation and I get 88 is the answer to this problem. Here's another example. Suppose we know that f of x is continuous and differentiable everywhere. Let's also suppose that we know that f of x has two roots. Show that f prime of x must also have at least one root. You know what to do. Let's see how you did. It's important to note that all we can say is f prime will have at least one root. We can't say it will have exactly one root. So this is a different kind of problem. But what we're going to do is we know that f has two roots, and let's suppose that those roots are called a and b. Then we know that f satisfies the hypothesis of the mean value theorem. So we take f of b minus f of a all over b minus a, and there is a c such that f prime of c is equal to that. But that's going to be 0 minus 0, so there is a root at c. Now it's important to note we don't have a value for that, we only prove that it exists. I also mentioned that it's possible to generalize this significantly. If we know that f is satisfying the mean value theorem and has three roots, we can then we can show not only will f prime of x have at least two roots, but f prime of x will have at least, f double prime of x will have at least one root. And you could work on that if you chose. We're going to close with a couple of facts here. If f prime of x is equal to 0 for all x in an interval, then it's constant. Now previously, you know, we knew that if f was a constant, f of x is a constant, the derivative is 0. But this is the other way about. This is saying if the derivative is equal to 0, then we know that f of x is a constant. Well, we're going to prove this using the mean value theorem. So f prime of x is differentiable because we said that's the if part. And so if we take any two x's in a and b, say they're x1 and x2, then what we know is that since f is continuous and differentiable on the whole of ab, it's also continuous and differentiable on this closed interval. That means the mean value theorem can apply to those two values of x. So we can get that f of x2 minus f of x1 is equal to f prime of c times x2 minus x1. But f prime of x is equal to 0 for all x in AB, so it is equal to 0 for C. So that means we put 0 here, so f2 is equal to f of x2 is equal to f of x1. That means we've shown that it is a constant function. There's a follow-on fact too. If f prime of x is equal to g prime of x for all x in an interval AB, then in this interval we have f of x is equal to g of x plus a constant, where that's some constant. Well, this is easy to prove because we consider h of x equal f of x minus g of x. Since both f of x and g of x are continuous and differentiable, then so must h of x be. Therefore, the derivative is this, and we said that that derivative had to be 0. That means, or had to be a constant, that function had to be a constant. So this is true, and so we have h prime of x is equal to 0. But that means that h of x is equal to a constant, and we plug in what h of x is, and we get our conclusion. This will be important when we talk about antiderivatives very soon. So, in closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless.